Properties of exponents. Now, this is going to be a big review. We've been doing properties of exponents for a while. It's a pre-algebra standard. We're going to go back to it and give us a little bit more review and practice, because it's actually a big part of, you have to have a really good understanding of this for not our next unit, which is radicals, but for our unit after that, which is polynomials. Okay, so properties of exponents, let's talk a few things first. My first is anything to the power of 0 is what? Anything to the power of 0 is 1. So that's sometimes a pretty simple fact that we forget about. Anything to the power of 0 is 1. And I'll show you a little bit of why. We're not going to put this in our notes because we've got too much stuff to write. But like if I put 3 to the first power, what does 3 to the first power equal? 3 to the first power is 3. 3 squared is 9. And 3 to the third is 27. Okay, so like this is an exponential function, correct? Because over here, my y values, my answers, every time are multiplying by 3, correct? As I go down, they're multiplying by 3. As I go up, what's happening to them? It's dividing by 3. 27 divided by 3 is 9. 9 divided by 3 is 3. 3 divided by 3 is 1. And if I look over here, this is 3 to the third, 3 to the second, 3 to the first. So what would this one be?
0.
So anything to the power of 0 is 1. Because if you follow that exponential pattern, to get back to an exponent of 1, in this pattern we divided by 3, well, 3 divided by 3 is 1. It's not 0. So anything to the power of 0 is 1. Keep that in your brain. Don't forget it. I'm going to even highlight it because it's easily forgotten. Anything to the power of 0 is 1. Now, the second thing that we just need to keep at the front of our brain all the time while we're doing these problems is when in doubt, write it out. If you cannot remember the shortcuts, or the shortcuts just don't make sense to you, if you expand it and start from there, it makes life a whole lot easier. So if you ever look at these problems that we're working on and you think, oh God, I don't really know, or you feel unsure of your answer and you want to check it, if you expand it, that's writing it out. If expand means to make it bigger. When in doubt, write it out. All right, I'm going to give you a problem. 3x to the third times 2x squared times 4xy times 2y to the third. Right? It's a lot of multiplication. It's multiplication of powers, correct? It's an exponent times an exponent times an exponent times an exponent. Yes? Okay. So if we talk about this and I look at this problem and I'm like, I have no idea. This problem's so hard I can't figure it out. When in doubt, write it out. So 3x to the third really means 3x, x, x. 3x to the third, correct? I expanded it. And 2x squared really means 2xx. Yes? And 4xy really means 4xy. That doesn't change. And then 2y to the third means 2y, y, y. And now I'm going to start collecting things that belong together. I'm going to start collecting items that belong together. So if I look, I've got 1, 2, 3, 4, 5, 6 x's. Do you agree? So if I'm going to squish those 6 x's back together, right? I've written it out, I've expanded it, now let's squish it back. What's an easier way of writing x, 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 x? X to the 6th. And let's look for other things to collect. So I've got y, 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 y. How many do I have? 4. And an easier way of writing that is y to the 4th. And last but not least, I have 3, 2, 4, and 2. And I'm not going to write 3,242. I'm not going to squish them together like that. I'm actually going to multiply because that's my operation here, correct? So what's 3 times 2? 6 times 4?
24.
24 times 2?
48.
And there's my answer.
Yep. You got it, Julian. You can often hear my voice in these.
So here's the rule. Here's the shortcut. When powers, another word for exponents, have the same base. What's the base of a power? The number. So like here it's x, right? Here it's x. Could it be a number? Could a number be a base to an exponent?
Yeah.
Yeah. Or it could be a variable. When powers have the same base, multiply the coefficients. What's a coefficient? The number in front of a variable. Multiply the coefficients and add the exponents. When powers have the same base, multiply the coefficients and add the exponents. So if I look at this original problem, when powers have the same base, multiply the coefficients. So if I look, 3 times 2 times 4 times 2. 3 times 2 is times 4 times 2, 48. And add the exponents. So I'm looking for the same base. So x to the third, 3, plus 2 is 5, plus 1 more x is 6. And 1y plus 3 more is y to the 4th. When powers have the same base, multiply the coefficients and add the exponents. Important. Next problem. I'll do this. Kind of give us some definition. 3x to the 4th to the 5th. 3x to the 4th to the 5th. 3x to the 4th to the 5th. So here's my rule. When in doubt, I don't know how to solve this problem right now. When in doubt, write it out. Expand it. So what does 3x to the 4th to the 5th mean? What does 3x to the 4th to the 5th mean? How could you, there are a couple things we can do. How would you expand 3x to the 4th to the 5th? What does 3x to the 4th to the 5th mean? Lucy?
3x to the 4th times 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 3x.
It means 3x to the 4th
5 times.
5 times. 3x to the 4th times 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 3x to the 4th. It means 3x to the 4th 5 times. So I expanded it. Could I expand this even more? Yeah, I can write 3 x, 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 x. And then 3 x, 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 x. And then 3, right? I mean, I could expand it more. However, I can stop here because did we just learn a rule on how to do problems like this?
Yes.
The answer should be yes, because it's highlighted right above it, correct? When powers have the same base, we multiply the coefficients and we add the exponents. So I'm going to multiply 3 times 3 times 3 times 3 times 3. What's 3 times 3? All right, so I'm going to cover those two up. That's 9, right?
Yeah.
What's 3 times 3? 9. I'm going to cover those two up. What's 9 times 9?
81.
Okay, so I'm at 81 and I've got one more. What's 81 times 3? So 3 times 3 times 3 times 3 times 3 is, you told me what, 243?
4, 3.
Okay. All right, I get that. I understand. There are a whole bunch of numbers, those coefficients. If I have coefficients, if I have big numbers in my problem, I'm just going to multiply them together, correct? Like, I can do that. That makes sense to me. That's regular math, right? But now what do I do? Add the exponents. I've got x to the 4th, x to the 4th, x to the 4th, x to the 4th, x to the 4th. I could write all of those out and then count them up, correct? Or I could do 4 plus 4 is plus 4 more, plus 4 more,
16,
plus 4 more,
20.
x to the 20th. When in doubt, write it out. If you expand it, it can be easier for your brain to look at in groups. But there's also a shortcut, if it makes sense to you. You by no means do you have to use the shortcut until you're comfortable with it. Or if you get your assignment back and you're missing a lot of problems and you've been using the shortcut, guess what you should stop doing?
Using the shortcut.
Using the shortcut, and you should go back to expanding it until you start seeing a pattern, because there's a pattern. That's all math is. That's all algebra is looking for patterns, right? If I look at this problem, where do you think 243 came from? Not where do you think, where did 243 come from? The coefficients. And we got 243 by multiplying the coefficients, correct? I did 3 times 3 times 3 times 3 times 3, correct? Which is 1, 2, 3, 4, 5. Look right here. 3 to the 5th. Where did this x to the 20th come from? The exponents, correct? 4 plus 4 plus 4 plus 4 plus 4, correct?
Mm-hmm.
Which is not 4 to the 5th,
4 times.
it's 4 times 5. So here's my shortcut. When powers have a power, meaning when exponents have their own exponent. When two exponents touch, right? When powers have a power, distribute the outside exponent so this outside exponent, which is a 5, is going to get distributed inside to every number, correct? It's going to get distributed to the 3, and it's going to get distributed to the 4. The coefficient, coefficient, the coefficient is raised to the power. The exponents get multiplied. When powers have a power, when an exponent has an exponent, you distribute the outside exponent. So that 5 comes inside to every number. The coefficient is raised to the power, so it's 3 to the 5th. But the exponents, the powers themselves, the little tiny numbers, it's not 4 to the 5th, it's 4 times 5. All right, here's your next example. 10x to the 6th, y to the 4th, z, over 4x to the 4th, y to the 10th, z to the 3rd. Again, that problem is 10x to the 6th, y to the 4th, z. And then the denominator is 4x to the 4th, y to the 10th, z to the 3rd. We don't know the rule yet. We haven't gotten a shortcut. So, since I don't know a shortcut, what can I do? Write it out. Because it's going to visually make more sense to us if we write it out. So we've got 10, 1, 2, 3, 4, 5, 6 x's. Then I have 1, 2, 3, 4 y's. And I have 1 z, correct? Over 4. And then I have 1, 2, 3, 4 x's. Then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 y's. And then I have 1, 2, 3 z's. I get it. Expanding your problem is terrible. But if you can't remember or the shortcut isn't working for you, does this work?
Yeah.
Yes. Okay, so if I look at it, I know if something's in the numerator and in the denominator, that means, like, let's pretend x is the value 2. So if I have 2 divided by 2, what happens? It disappears, right? It cancels out. So I can cancel those out. X divided by x cancels out. X divided by x cancels out. X divided by x cancels out. And x divided by x cancels out. Anything else cancel out? Oh, I can cancel out one set of y's. Anything else? Another set of y's. And one more set of y's. And one more set of y's. Anything else? One more z. Anything else? No. However, I can look at this guy. Do you know anything about 10 over 4? 10 over 4 is also 5 over 2. What else is left in my numerator? X times x, and x times x is what? X squared. What's left in my denominator?
6y.
1, 2, 3, 4, 5, 6. So y to the 6th. Anything else?
Z to the second.
And z squared. And that's my answer. But there's a shortcut. Ariana told me that I just simplified my coefficients, right? 10 over 4 can be simplified to 5 over 2. But where do you think this x squared came from?
Subtracting the
6 minus 4 is 2. So that's where my x squared came from. Where do you think this y to the 6th came from?
4 minus 10.
I subtracted, but hold on. 6 minus 4 was 2. 4 minus 10 is negative 6. How come this isn't a negative 6?
Because down the bottom part though.
If you subtract and you get a negative value, it tells you that that denominator or that exponent belongs in the denominator. What's 0 minus 3? Shouldn't it be negative 3? How come I have a 2?
There's always an imaginary one.
You cannot forget that there's always an imaginary 1 that you have to add into it. So our shortcut rule for division is when powers are divided by powers, and we have to do the same base, right? You can't, if it was x to the 6th over b to the 4th, would those cancel out?
No.
No, they have to have the same base. Subtract the exponents. Meaning the numerator minus the denominator. Simplify the coefficients. When a power is divided by a power, meaning they have the same base, subtract the exponents. Subtract the exponents. Numerator minus denominator. You also have to simplify the coefficients. I'm going to tell you right here, right now, especially in the beginning, don't forget exponents of 1. That's huge. Don't forget exponents of 1. That's the biggest mistake, is you start using this trick, this rule, and you forget that there's an exponent of 1. Also, negative exponents move down. Right? What does down mean? I should probably say a mathematical word there, huh? To the denominator. Has a lot of rules, I get it. Lots of shortcuts, but if these shortcuts don't work for you, you can always write it out. On page 51, we're going to do a few examples. On 51, we're going to do a few examples. Here we go. All right, there's the first one. There's 2.